value using data that's available. I know that you're all here to listen to Rayid rather than to me, and Rayid, welcome. I'm here to listen to you too, so I'll keep quiet now and ask you to take over and speak to the audience here. We are truly honored to have you here as part of the initiative that we are starting in working with universities closely in Punjab. And I know, of course, you have a close association with Punjab too. So you feel the same pain that we have, that, we want to see great technology come out of this state. So I'll pass over to you, Rayid, and thank you again for being here.
No, thank you. Thank you very much for the invitation. Let me get my slides set up quickly. How much time do I have for that? 30. Okay.
You have an hour and a half. I know it is 11 o'clock at night for you, so we've got an hour and a half. You can speak for an hour, take questions if that's okay with you.
Absolutely, and also for those of you who are listening, feel free to jump in the middle and ask questions if you want to, either on chat or also depending on the sound verbally. So I'm happy to take questions throughout as well. And let's see. So. Okay, so let me share my slides.
Yep, super.
Okay, perfect. Then 1 second, let me move things. Okay, perfect. Good. Yeah, so thanks for the very kind introduction and the invitation. I thought what I could do was, I'm sure you guys are going to be bombarded with talks over these next few days, lots of people talking at you. So I thought I'd mostly keep my talk to lots of examples of what's possible, what can be done. Usually sort of when we, at least for a long time, whenever I still have, people talk about machine learning and AI and data science, the kinds of things that we hear about are a lot of things that are very nice to have, but not critical, right? So shopping, and that's also it's probably the biggest recent use of data in India is all these different companies selling you things, right? Whether it's Walmart buying a bunch of stores, or Amazon coming in and coming out, or all the other e-commerce companies in India, and that's wonderful, right? Some of them are actually useful for people, but a lot of them are not necessarily helping people, and same for advertising, or in finance, and all these different things that they're not the most critical things that we need in the world, and yet a lot of the people are working on these things. So what a lot of the things I want to the examples I want to give are things that affect sort of daily, everyday life, but where data can play a role in kind of helping improve things, whether it's education, whether it's healthcare, whether it's public safety or transportation, and all those sort of things that affect us every day. What is the role data can play in dealing with that, in improving things? And so let me give you a few examples of projects, right? So one of the first, and this is, again, unfortunately, this is a problem pretty much most countries in the world, where there are a lot of students who start school, but then don't have the support, don't have the programs in place to help them do well, to help them graduate high school, to help them get into college, to help them do well in college. And a lot of universities and schools and programs exist to help them. It's just there's a mismatch. There is often these universities or these programs don't know which students need help and what type of help. And so this is something we've been working on with several different schools, um, primarily in the US, but also some work in South America on identifying which students need extra support, extra help to graduate school on time. And it's not just sort of high school, it's like we've worked on different projects where one of them was about which students, when they are, when they turn 8 or 9 years old, which of them will not get to reading level at the right grade? And if they don't get to reading level, then they're not going to be able to catch up. So in this case, the school system had access to a few different programs. One was really expensive and they could only give it to a few people. Another one was less expensive, they could give it to more people. And another one could be given to everyone. And so the question they came to us with is, can you help us figure out which students need the more intense program and which students need the second level and which students the third level? And can you help let us know early enough? Because if you tell us a week before, we can't get them to learn how to read in a week. So if you can tell us early, if you can predict which children are likely to not get to the reading level, then we can use that to figure out who to give this program to. And the same thing applied to students who might not be able to graduate, from high school. And the idea was, again, if we can tell people early enough, right? So it turns out that if you're, a lot of you are teachers, right? So students who might be at risk of not graduating or not doing well. That's a computer probably cannot do better than your students. But if a school or a country has to decide and compare all of these students, figure out which ones are most at risk, it's very hard to compare and standardize that. So a lot of these systems are really able to help you figure out how to prioritize, how to combine. The students who don't have good grades, they're at risk, but good grades when and what time, and can you predict early enough? And so in this case, the idea was we've been working with a few schools to help them predict early, give them an early warning system to help them understand which students are at risk and then what to do. Right. So that's kind of one recurring example. Another example that some work we've been doing, and this is around health. Actually, I'll come to this one. So this is some work that we're doing in the US, again, in Chicago. And so a lot of the homes that are more than 30, 40 years old. So in the US, for example, every home that was built before 1977 has paint that has lead in there, the metal. And lead is fine if it's in the paint. What happens is that when paint gets old and it starts coming, dust comes down on the ground, children, when they start crawling, they pick up dust and they put it in their mouth and it goes into the blood. And once it gets to your bloodstream, it has pretty bad outcomes. Memory issues, brain damage, IQ issues, hearing loss, all sorts of issues. And the bad thing is that you can't fix any of those things. Once you get lead in your bloodstream, that's it. You can't do anything to fix it. So at least in the US, the way a lot of health departments deal with it today is they test kids for lead poisoning. And when they find a kid that has high level of lead, they then try to figure out, okay, let's go check their home. And if their home has lead, then we'll try to fix it. Except if they already tested positive for high lead, then it's too late to do anything. So they wait until somebody gets lead poisoning and then try to fix the problem, which is useless for the child who just got lead poisoning. It's useful for the future children who are going to live in that home, but it's pretty much a waste of, this kid is already gone. So again, they came to our team and said, look, we know we're not doing a good job of preventing lead poisoning. We are too late, and we react to something as opposed to being early. So can you help us figure out, again, ideally, we would take every home in the country that is old, that has lead paint, and fix all of them. That's the ideal solution. But we don't have the resources to do that. We only have resources to inspect a small percentage of the homes today, and if we find lead, to fix them. And so ideally, we would get more resources and fix every home. But today we cannot do that. So how do we prioritize the homes that we should go to first? And so the simple solution could be, well, how do we, can we just make a list of homes that are old, that have paint, that haven't been replaced, and let's just fix all those homes? Well, that's too many homes. So then we say, well, okay, maybe we reduce it to the homes that have that paint and have children, because if there are no children, it doesn't affect adults very much. So we reduce it down. Well, that's still a lot of homes, but more importantly, just because there is no child in that home today doesn't mean there won't be a child tomorrow, because these people move around. And so that's not good enough. So then the idea was, how about we take every kid that gets born, and can we predict if this child is likely to be lead poisoned living in this home in the next few months? And if yes, if it's high risk, then we prioritize that home. If no, then we don't prioritize that home. So what we built that system, and so step one was really trying to figure out, can we predict if this kid will get lead poisoning? Step two was to figure out, does removing the lead, does doing an inspection and trying to figure this out, does that reduce the risk of this kid getting poisoning? So we built a machine learning system to do step one, and then we ran a randomized experiment, a trial, to test and see whether we can do a better job than what they were doing today. And it turns out that we could. There are more details and more papers and things like that. And so that system is now running in Chicago. The third thing that we ended up doing in this case was also worked with hospitals to implement this into their medical record system, so that when a pregnant woman goes in for a checkup, the system is able to predict the kid that's going to be born in a few months will be high risk. And if I can tell the health department this early, then they have more time to allocate resources to figure out where to send these inspectors to, and try to solve the problem before the kid is born, to make things more lower risk. So it's another example of where, again, having access to this data early, if we can give people this warning with enough time, then they can fix the problem. Same thing. So this is another example of another problem, and even though sort of this is about police departments, being pretty bad, doing things that they shouldn't be doing, it's not just a problem in the U.S. Unfortunately, it's a problem in a lot of places where police officers, do things that they shouldn't be doing, and that involves sort of shooting. It involves injuries. It involves all sorts of horrible things. So again, the idea behind this was, today, it turns out actually in the U.S. that every large police department has a system in place that is supposed to raise an alert if a police officer is at risk of doing something in the future like this, shooting people or causing injuries, except none of those systems really work. And so when we started working with these police departments, we worked with them to figure out, can we build a system that gives, again, a police department early warning that this police officer is going to be high risk of doing something bad. So they should try to stop it early, try to prevent that from happening. And again, that system is implemented and working in a few different departments. Let's see, let's take another example. So here, actually, let's go back to the first example that I skipped. So this is a problem where what ends up happening is, you may have heard about some of these things. And so some of these examples, I'm starting with US because that's where a lot of my work happens. But these numbers are going to sound horrible if you haven't, if you don't know these things, right? So in the US, about 11 million people go through a jail in a given year. This is 1 year. And this is not, so the way US system is structured is you have prisons, which are kind of larger, where people go for 1 year, 2 year, 3, 5, 10 years. And then there are jails that are smaller that people might go for a few days or a few weeks. They get arrested, they get put in jail for 11 million people end up in jail in a year, which is, and the horrible piece there is that 2/3 of them suffer from mental health issues. And a lot of the people who end up going to jail have mental health problems. And what they need is help and mental health support rather than being put into jail. And so what ends up happening for a lot of these people is they go to jail, they get released, and then a few weeks or a few months later, they end up back in jail because they have these mental health issues. And then they get out and they go back. They keep going around. And so a lot of the different states in the US are trying to figure out, how do we can help give them the help that they need rather than put them in jail? How do we reduce their risk of going back to jail? And how do we figure out what they actually need, which is the help that they need? So this is some work we've been doing with a state in the middle of the US, Kansas, and they came to us with the same problem. They said, we have a high rate of people who go back to jail. And we think a lot of it is because of mental health issues that they have. We have, again, some limited resources that we can go in and provide them with mental health services, but we only have resources in this case for a couple of hundred people every month. So how do we pick the 200 people? How do we pick the ones that if we just go and give this random people, that's not going to be very useful. We want to kind of make sure that we allocate it to people who need that help. And so that's sort of the first question that they asked. So what we did was, we first wanted to see, can we figure out who's going to be returning, who's going to be arrested and going back to jail. And it turns out that after combining all this data, we had data from jail system, we had data from the hospital system, we had data from mental health, we had all these different data sources. We could put it together and build a system that was extremely accurate at predicting who's going to go back to jail. But the point of this was not to predict who's going to jail. That's not very difficult. In general, if you sort of look at a lot of these systems doing machine learning, we are generally very good at doing prediction, but often prediction is not the thing to do. What we're trying to do is prevent them from going to jail, not predict who's going to go to jail. Same for students, right? The goal is not to predict who's going to graduate or not graduate. The goal is to help them graduate. So in all of these types of problems, there is one piece, which is what computer science and machine learning is very good at, which is often predicting. And the second part is changing the behavior, which is not about using machine learning. It's really about looking at different types of programs in place. They're looking at different types of interventions of different services and seeing which service is effective at changing what these people are, changing the outcomes, not necessarily just predicting, right? So in this case, we first looked at, can we predict who's going to go back to jail? And it turns out, yes, we could. So the second step was providing them these mental health interventions. Does that reduce their risk of going back to jail? And so how do we test that? Well, so we started, again, a randomized control trial, which was in June 2019. And what that trial was, is we took the list of people that we have, we predicted their risk of going back to jail, and then we had the state, the county we were working with said, we can help 100 and something people every month. So what we did was, because they could only help 150 people, we gave them a list. From this list, we selected 150 people, and we asked them to go and do mental health outreach. And then every month we would run the system and we'd give them this list. And so what we're now getting this data back is we're looking at, of the people they helped, what percentage went to jail, and of the people they didn't help, what percentage went to jail. So what we're trying to test is, does helping these people reduce their risk of going back to jail? And if it does, then this intervention is really effective at doing it. The second thing we're trying to do is we're trying to figure out, well, does it help everyone, or is it really much more effective for high-risk people, medium-risk people, low-risk people? Because if it really works for high-risk people, then that's great. But if it only works for low-risk people, then we have to figure out, how do we help the people who are really highest risk? Because it's okay. It's not bad to help people who are low risk of going to jail. If you're 1% likely to go to jail again, it's still better. It's still good to help you. But it's the person who's likely to go to jail 80%, 90%. It's probably more important to make sure that we don't miss those people. So that trial is running right now. I don't have answers today right now, but we're going to be getting data back up to next year, and we'll measure both the overall effectiveness as well as who does it help, who does it not help, so we can then focus on those people and try to create new programs for them to make sure that we can help everyone. So another few examples. So this is, again, there are different types. So a lot of the examples I gave now are what I call sort of early warning systems, right? Systems that where today we wait until something bad happens and then we try to fix it. And that doesn't usually work, right? Once somebody has not finished school, it's hard to get them back and finish. Once somebody has gotten lead poisoning, it's not possible to fix it. Once somebody has gone back to jail, it's kind of hard to, again, help them. Once a police officer has done something bad to somebody, it's hard to undo that, right? So damage is already done. And so those are kind of early warning systems. When something bad is, today we wait until something bad happens and try to fix it. But if we can use machine learning to figure out and give early warning to these organizations about these things happening, can they design programs to prevent the adverse events, the bad events from happening, right? So that's kind of one class of problems. A second type of problem that comes up where a lot of these types of technologies are really helpful is inspection type programs, right? So you're familiar with sort of a lot of organizations, a lot of agencies, government agencies that do inspections. And so some examples, inspecting building for safety issues, or inspecting workplaces. So this is some work we were doing in Chile a few years ago, where a lot of the workplaces are not safe for people, right? So those workplaces could be offices, but they could also be mines where people are underground and sort of mining, and it may not be safe. And so the government agency there was responsible for inspecting these workplaces to make sure that they're safe. And the question was, how do we design these inspections? Usually they have a large number of offices or workplaces they could inspect, but they only have they have resources to inspect a small number. How should they pick a small number? And this is a common problem. It's not just inspections, but if you look at, taxes, there might be fraud, or for other types of, credit card fraud, or where you cannot audit everything. You're going to pick a small number to audit. So how do you pick that small number? And that's where, in this case, we've been working with different organizations to help them improve their inspection process, whether it's for health and safety issues in housing, or whether it's, there are factories, right? When they produce chemical waste, they sometimes just dump them in the river next to the company. And that's not good for the people who are going to be, using that to get their water. So again, there are many, many, many such facilities, many such companies. The agencies responsible for inspecting them, they only have resources to inspect a few of them. How should they pick them? And that's again a problem where we can figure out which agencies, which facilities, which companies, which workplaces are high risk of violations of not meeting the standards, and then prioritize inspections to those facilities or companies or houses and buildings and offices. Here's another example, and this is some work a couple of years ago. This was in New York, and one of the things. So what happens in a lot of buildings in New York is that people are living in apartments, flats that the rent is controlled, where the government says you cannot increase the rent by more than this amount every year. And what happens is a lot of people who own those apartments or flats want to increase their rent a lot more. So they keep harassing the people living there to try to get them to leave, to try to increase their rent. And some of these people don't know that their rent cannot be increased, or they don't know that they can appeal against it, and they don't know what their rights are. So they often, get scared and then they leave. And so what the government wanted to do was to make sure that they could focus their efforts and tell people who might be at risk of this that they have access to these legal resources. They have free legal resources that they can get access to. And so they wanted kind of our help in seeing, well, we can't go. The way they were telling people was they were going to every house and knocking on their door and saying, have you been harassed by your landlord? And if you have been, here are some resources that exist that can help you deal with it. But in order for them to go through every home, every building, every apartment, it would have taken them a long time. So what they came to us with was asking for help, was a way to, again, how do we sort which home to go first, which people are most likely to get harassed. And if we can start with those, then we can get to those people sooner who are higher risk than lower risk. And yeah, so that's another example. This is a very different example, but also something that should be familiar to you, unfortunately. And this is again water pipes breaking. And every time water pipes break, it happens a lot. And when it happens, of course, it's not convenient because you don't have water in your house if the water pipe outside your house breaks. But not only you don't have water, but the stores in your area don't have water, which means you can't go and buy things that are refrigerated or that are frozen because all those systems are gone. And then somebody has to come and they have to dig up the street and they have to fix it, and it takes time and it costs money. So this is some work we were doing with a small city in the US on, can we look at previous data? Can we look at historical data to, again, identify and predict which pipes will break in the future? And if we can predict with high enough accuracy which pipes are going to break, what they can do is coordinate, when a street is supposed to get repaired or the street is supposed to get fixed, they can just dig a little bit deeper and try to also take care of the pipe. Or if it's not high risk of breaking, but sort of medium risk, they, instead of tearing up the street and kind of doing everything again, they can put in sensors to monitor it in case something breaks. So it sort of helps them plan how to coordinate with when the roads are being rebuilt and based on the risk of a pipe breaking. Here's another example of the use of sort of machine learning and data. And this is some work in Indonesia, in Jakarta. And so, this traffic should look familiar, again, unfortunately, right? And Jakarta is, again, a massive city, one of the largest cities. And unfortunately, what ends up happening is that there are a lot of accidents, traffic accidents, and a lot of people die. A few thousand people die every year in Jakarta in traffic accidents. And so what they wanted to do was, what the thing they were struggling with was, they were trying to figure out what is the underlying reason? What is the underlying cause of these accidents? Yes, people might be driving fast, but what is it that's really causing these accidents? Is it, there are issues with the streets, is it issues with traffic lights? Is it because people are kind of crossing the street in the middle? Is it people are not following the law? And so they wanted to figure out what was happening. And so in order to do that, what they did was they put in cameras on traffic lights. So they put in about 5,000 cameras in the city on traffic lights to collect data. And what they sorry, I just noticed a question from one of the previous things on somebody's asking, what was the data on the basis of which you chose 150 people, and how did you get that data? So in that case, the number 150 was based on this government agency saying we can help 150 people. That's how many resources we have to go out and help people. The way in which we selected the 150 was we took everybody who had been to jail in the last 2 years, and then we took everything we had about them, and we built a model that predicted what's their risk of being arrested and going back to jail in the next year. And then we took the 150 highest risk people that we predicted, and we chose those as the people to focus on. So the idea was that how do we focus our efforts on the people that are most likely to go back to jail, and that was the way to select that. But just to kind of keep in mind is, just because they are high risk of going to jail doesn't mean that this program can help them. So we have to kind of test. We have to test both things. We have to test: are we good at predicting who's going back to jail? And the second thing is, are we good at preventing if they're going to go back to jail? And if we are good at predicting and not at preventing, then we're not helping these people. But if we're not good at predicting, then it's hard to focus on helping them, because we can't even figure out who it is. So we have to help everyone. So the point of prediction is to reduce the focus, to increase the focus, and say, okay, if we want to reduce this, we have to first figure out who's going to go back to jail and then focus on them. So both of them are kind of important, and one of them by itself is not enough. So so coming back to this one, the idea was that they put in cameras, and as soon as they put in cameras, it's kind of obvious, right? They realize, oh, now we have video coming in 24 hours a day from these 5,000 cameras. We don't know what to do with it. What they wanted to do was basically a database, a spreadsheet that told them what was happening before an accident happened. So what they wanted to know was things like, oh, there was this food vendor going in the middle of the street, or there was a person crossing in the middle of the traffic, or there was this motorcycle that was overloaded and it fell over, or over here, like a car that was going in wrong direction, right? So again, we're all unfortunately familiar with all of these things. We see them every day, right? But if you the videos, I mean, we can look at them and figure that out, but we don't have software that can detect all of these things. And one of the interesting things, again, for a lot of you who are, working in these areas or interested in these areas, a lot of these types of systems exist, but they exist for traffic in the US or traffic in Europe. And none of these things exist that will work on this data, because there is no category to detect, somebody selling food on the street. There is no category for this type of a motorcycle, because in the US, you don't see motorcycles like this, right? So even if you look at even if you apply this, there are these models that exist to detect objects from traffic. If you take a model for a bus and apply it and try to use it with a bus in London, it doesn't work, because the buses are completely different. So that's something that's a big issue right now, is if you take all these things that are developed, for US, they don't really work anywhere else in the world. And people might say, oh, this is a solved problem, but it's not, because just because it works for the US doesn't mean it's actually a solved problem. So that was kind of our first piece is, can we modify the system to detect these types of things? And once we've done it, what we want to do is sort of detect, these types of things happening over here. And ideally, so here's, what we wanted to sort of find was things like, what is the object? Is it a car? Is it a motorcycle? Is it a person? Which direction is it moving in? Is it going with the traffic, against the traffic, on this side? And then where is it? Is it on the street? Is it on the side? Is it in the middle of the street? And so once we could do that, we could then start detecting these types of events. So this is, as you would imagine, this is a two-way street. But, people go around and try to pass. And so what this system can do now is detect these things, right? And say, it happened at this time and this time and this time. And now if you can turn this into a spreadsheet, and you can see, every time this happens, there is an accident that happens in the next, 1 minute in this area. And so you can start saying, oh, maybe what we need to do is put a divider in the middle of the street so people can't come around, that it stops them from doing that. And maybe that's the way to fix it, right? So this project was not about predicting an accident. This was about taking these videos and turning them into data that an analyst could analyze, and then look at what are the factors that lead to different types of accidents happening. So those are kind of some examples of where, data, machine learning, AI, all these different things are being used to deal with different issues in education, in healthcare, in sort of public safety and transportation. And one of the things as we sort of think about this is, right, some of that's common here is we're sort of trying to do a few different things, right? One thing we're trying to do is we're trying to understand how people behave, what has been historical behavior of people, what is the behavior of students, what kinds of students graduate on time, what kinds of children get lead poisoning, what kinds of things happen in the past. Second thing we're doing is we're then using that information to predict what's going to happen in the future. Which children are likely to get lead poisoning, which police officers are likely to do bad things, which students may not graduate school on time. And the third piece that we're then doing is we're trying to change or influence their behavior. And this is, in general, this is a very common thing that happens all across the board, right? It happens in unfortunately in marketing, right? Where people try to predict what you're going to buy, and then maybe try to convince you to buy something else that might make them more money. Or they might try to predict what movies you might watch or what books you might read, and then try to change your behavior to watch a movie that might make Netflix more money. Or it happens in elections and politics, right? We try to understand voters. We then try to predict if they're going to vote, who they're going to vote for. And then we try to change their behavior. We try to see if we can make them more likely to vote, or we can change who they're going to vote for. So this cycle is a sort of a very common thing that happens over and over again, where we try to understand people's behavior, we try to predict their behavior, and we try to change that behavior. And this cycle sort of continues, right? And the question is sort of, how do we design these systems so that they result in making things better and not worse? Because you can use this model to also do bad things, right? You can sort of, again, figure out who's going to vote and try to change their behavior so that they don't vote. Was there a question or sorry? Okay, I'll keep going, but stop me if you have a question. Because one of the things to keep in, sorry, Sarah, did you have a question?
Yeah, right. I have a question. So, in a lot of the examples that you were giving, police brutality or people reoffending and so on, if we look at historical data, there's a concern around bias, right?
Yep.
And how do you deal with that
Yeah.
within the cycle?
Yeah. So I'm gonna get to that in a minute, but I think one thing to think about is there is clearly a bias in who the police does horrible things to. There's clearly a bias in who ends up going to jail more often than others. Um, and the question is, in these types of systems, you actually want to predict the bias because you're trying to help these people, right? So if you ignore the bias, if you say, oh, well, they might be biased, but I'm going to ignore this bias, then you will miss the people that are going to be affected. So you actually want to use that bias. Ideally, the bias doesn't exist. And ideally, you sort of fix society so that these things don't happen. Unfortunately, that's going to take some time and we should work toward that. But right now, what we're trying to do is say, look, the system is going to affect these people. What we're trying to do is get to them before the system gets to them. So if we don't do anything, this person might get arrested tomorrow and then go to jail. But if we can predict that this person might get arrested tomorrow, can we help this person today before they get arrested? So we want to we want to use this information to try to sort of to help them before they sort of get sucked into the system. But I'll come to the point of sort of where some of these biases might come from and how we deal with it.
Thanks, Ryan.
So kind of thinking about all of these examples, right? There's sort of three things in common there. One thing that's common among all of them is we're not making automated decisions. We're not sort of have a computer that predicts who's going to go to jail and does something, like presses a button, right? It's what we're doing is helping a person help another person. So this person's job is to figure out how to provide help to this person. We're just making this person's job hopefully easier. Same for, if there's a social worker or a health worker or somebody working in a school, their job is to help the students, and we're building these systems to help them rather than make automated decisions. The second thing that's in common in all the examples I gave is sort of this: we have limited resources, and it's unfortunate that we have limited resources, right? Ideally, we have enough resources for everyone, but that's not the case today. So the idea behind these systems is who do we prioritize and how do we prioritize them? And because of that limited resource issue, we have to figure out how do we balance different goals. And so, one way of thinking about of this is actually let's take an example right now, right? Like, so right now, we're all dealing with the effects of COVID, right? And someday in the future, there will be a vaccine. And when there is a vaccine, we're going to have to decide if we get 100,000 vaccines, limited resources, who do we help first? Who should get the 100,000 vaccines? So actually, yeah, let me ask everybody here, and you can use the chat. Who should we, if we have 100,000 vaccines in, let's say, all of India for the first 6 months, who should we give this vaccine to first? So somebody said highest risk. Somebody said Delhi because you live there. Highly vulnerable people, healthcare workers, doctors, diabetics, adults. Yep. Primary contacts. What do you mean by primary contacts? I think it was Jyoti. people above 60 and below 10, people at high risk, people who are going to die, newborns. Yeah, so basically, those are all really good ideas, right? So, and I like the last, one of the, so most people are sort of saying, are different ways of selecting the people who will most likely, let's say, die if they got it. Right. So we're basically saying, so a lot of people are basically saying that people who are going to be at risk of complications, people who are going to be at risk of, sorry, I think I'm getting a lot of echo.
I think there's a unmuted mic. Nampreet, there's Jyoti, can you?
Got it. I think. Yeah. So step one is people. So one thing to make sure is, the first step is people who are going to be high risk of complications or death or things. So that's older people, people who have other conditions, whether they have serious conditions, people who other types of comorbidities and other types of diseases. So that's one. But the second is, and then people say, some people are also saying, well, maybe people who are going to come in contact with all people who are going to be coming in contact with a lot of people who have COVID, right? Because they're going to have a high risk of getting it. And so there are a few ways of thinking about it. One is the vaccine's role is to prevent you from getting COVID. And so if you have limited resources, you can sort of take a few different approaches. You can focus on the people who are highest risk, and that's one approach, right? You can say, okay, that means that we're going to be very efficient. We're going to take everyone, pick the 100,000 people who are highest risk of complications, and we can figure out what that means, right? It means different type of diseases. If it means age, it means other conditions. Let's say all of those highest risk people happen to be in Delhi. So we just give the highest risk, and let's say the rest of the country, we don't do any vaccines. Is that good or bad? So why is it bad? Because we're if all the highest risk people live in Delhi, because it's a dense city, there's a lot of people who live in a small space, and they come into contact with each other, and so they're much more at risk, and other people are lower risk. So, but they're less vulnerable. They're vulnerable, but if we are sure that they're less vulnerable, is that still a good or a bad thing? Right. So yeah, so part of it is, part of it is, the question is, what do we want as a country, as society? What do we care about? Do we care about focusing on the highest risk people? Because if we just gave vaccines to 100,000 people in Delhi, we know other cities are also going to have, other cities have COVID, and people will die there. And that doesn't seem like a fair way of allocating resources. It might be efficient, but it may not be fair. And so the question becomes, what do we care about? Do we care about is the idea to allocate? So another thing you could do is you could say, well, we have 100,000. So what we're going to do is take all the different provinces, all the different states, and give every state equal number of vaccines. And then they can give it to, the top, some number of people in each city. And so that means that you're allocating it in a way that's distributed equally, but that might mean that only 1% or only 0.1% of the people who need it get it in Delhi. but maybe in a really small city, 30% of the people who need it get it, right? So that doesn't seem fair either, because you're saying, well, why should this other city get 30% of their people get saved and only 1% of the people get saved in Delhi? That doesn't seem fair. So the question is, all of these, they're very different ways of allocating. And the big issue is that data or machine learning isn't going to give us an answer. It doesn't tell us which one is more fair, because you could say I could distribute it equally.
Hello.
Yeah. Go ahead.
Sumit, do you have a question? Sumit? Okay, I think that was probably by mistake. Carry on, Ryan. Sorry.
Okay. Yeah, so somebody is saying, well, we can give them the ratio. So for every city, we know how many cases they have. And so maybe we can give them, if we can give 1%, if the number of vaccines are, let's say, 0.1% of the overall population, maybe we can give every city's 0.1% of the number of their active cases. And that would be one way. So you could be fair according to city, but what about other things? What about gender? Maybe all the ones that get given to males because they have to go to work, or maybe all the ones given to female because they're interacting with other people, high risk people more. And so there are many, many, many different ways. And we can justify each way of being fair to certain people in certain ways. And then the question is, what do we actually want to get to? What do we actually care about? And in these types of questions, again, a lot of this, the technology isn't going to help us give the answer. It's something we have to discuss and figure out, what do we want? And what outcome will we be happy with? Is the outcome that we save the 100,000 most vulnerable people, or that we, spread it out in different regions, or we didn't, so let's go back to some of the other examples we were talking about, right? And so what we have to kind of figure out is, let's say we built the system to identify, let's say we built a system to predict who's going to be most vulnerable, right? And let's say we use machine learning to build a system like this, and we gave everybody a risk score and said, this person has the highest risk score for vulnerability, this person has the lowest risk score. And we did that for the entire country. Now, the problem is that a lot of these systems that we build using machine learning are not going to be accurate. They're going to make mistakes. And to Saurabh's question before, it's these systems are going to make mistakes in biased ways, right? So for example, let's say I build a system to predict vulnerability let's say the system is saying, what's the probability of somebody dying if they get COVID? And I gave everybody a score based on that. What if it's really bad at predicting the probabilities for women? So what it does is it gives women a lower score because it's looking at historical data, and it's using that historical data to build some model and it predicting. And let's say my system is really bad at, it just always under predicts the risk for women. Well, if I use that system to allocate vaccines, I'm going to say, oh, women are not high risk. All these people are high risk. I'm going to be very efficient, and I will give all the high risk people the vaccine, and I will miss all these women, and that's going to be bad. And so how do I figure out that my system has that bias? And how do I figure out what the reason for that bias is? How do I correct for that bias? And how do I design a system that leads to equal access for everyone and equal outcomes for everyone, not better for certain groups, whether it's male, female, whether it's by age, whether it's by geography. So that's kind of the piece I want to talk through, is all these predictive systems are going to be incorrect. They will not be perfect. And if they were imperfect randomly, where sometimes they're better for certain people, sometimes they're better for other people, that would not be good, but it would not be horrible. But often these systems are not equally bad for different types of people. They end up being much better for certain types of people and much worse for other types of people. And that leads to allocation of resources that end up being biased and hurting certain types of people more. So So that's let me kind of give you a little bit of why that happens, right? Or what we can do to deal with it, and I'll talk a little bit about why that happens. So so let's actually skip through this, right? So why do these types of biases come in our system? Well, the first reason they come in is because in general the world is biased. The world is not fair, and because the world is not fair, the data that we get from the world is not fair, right? So let's take, you know, um, take students who might not graduate from school. Well, what ends up happening is in a lot of our students who have money or parents who have money will, if a school is not providing the support, parents who have money will find extra tutoring, right? Extra help, and get their children to go through that extra help, and they get really good grades, right? So if you have 100 students in the same class, and they might be facing the same issues, people with more money can bypass that system and are able to do well, and students who don't may not be able to do well. Now, when we get data about these students, we don't actually see these other things, right? All we see is, oh, this person was taking these courses, they had these available, and these people did well and these people didn't do well. What we don't see is what's happening outside. We often don't have data about their home. We don't have data about this outside school stuff. And what that leads to is our system getting biased, thinking, oh, most of these students did fine. So let's assume that this school is really, the system, when it builds the machine learning model, it doesn't have that extra information. So that's kind of one issue, right? That's an example. The other one is that we often try to use data sources that are not perfectly fair, right? So that's been happening a lot with, let's say, so right now it's happening actually a lot with data that people are using to do analysis for COVID. Or actually, it happens a lot actually with social media data, where one of the common things a lot of people are doing is when a natural disaster happens, right? When a hurricane happens, or a tornado happens, or a tsunami happens, or an earthquake happens, what some of these organizations are working on, and so actually was working with some people in Bangladesh and Nepal, where when these natural disasters happen, what they're trying to do is say, oh, can we look at social media data? Can we look at Twitter to figure out what damage happened in small towns and small villages? Can we figure out what types of people were affected, what things were damaged, how many homes were damaged? And the problem with using that is that is not complete data. It only is data from people who use social media, and it's only data that they are reporting. So maybe if there's a bias in the type of people who use social media and Twitter, then you only see the data from their areas. And if we use that data to build our system, then we'll miss the people who are not reporting things. So often our data is biased. And where it's happening in COVID right now is there's a lot of people doing analysis on, when COVID started, certain places got shut down, governments decided to, place these restrictions and lockdowns. And what they're doing is they're getting data from mobile phone companies to look at how people moved around. What people who live in this area, where did they go? Where did they stop going? How did their behavior change? Now, the problem is this data that they're getting is not for everybody who lives in a city or in a country. It's from a company that has some sample of the data, people who use smartphones, people who have smartphones that have location enabled, and people who use certain apps that collect that location data. And so it has a very specific type of bias in there. And that bias leads to us thinking, for example, you might say, oh, we want to give this vaccine to people who are coming in a lot of contact with other people with, who might be at risk of COVID. And if they're trying to figure out coming into contact with this mobile phone data, then if people in your surroundings might be high risk, but they just don't use mobile phones, the government might think, oh, you're not very high risk because you're not coming into contact with anyone of getting COVID. So we're not gonna give you the vaccine. We'll put you lower down. Except you are coming into contact. It's just the mobile phone data doesn't show that. So that leads to the prediction of your vulnerability, of your risk you get scored lower, and you might not get the vaccine, right? So that's kind of on the data side. Then there's sort of people like us who build these machine learning systems. We often make choices when building the system that result in bias for the system. So for example, one of the common things that happens is, if you're familiar with this topic, this thing called record linkage, right? Where we link data about people together. So when you get data about you get data about a bunch of people, you get data about the same set of people from different sources, and you try to link the two. And if you don't have a unique ID, you're looking at you're using their name, you're using their address, you're trying to link people together. Sometimes, that's not perfect. It's rarely perfect if you use sort of nicknames, or if you have long names and it gets mistyped. So if you miss people, then you might not know what's going to happen to them. You sort of lose data about them. Sometimes you link people, but it's not the same person. They have similar names and you link them together. And that means that you added information about them, and that leads to bias later on. Another thing that we do is, when we build these systems, sometimes let's say we don't have somebody's, let's say your COVID vulnerability is based on your weight, how much you weigh, right? That's might be a factor. And so let's say we get data of a lot of people, and in the data we have a lot of, let's say we have 70% in the data we have are men and 30% are women, and we have the weight missing for maybe 10% of the people. And so what we typically do is we take the missing weight and we take the average of the entire data set and we fill that value. But now if you have a weight missing for a female, and you took the weight for everyone, took the mean for everyone and put it in there, now you've made this record for this female look more like a record for a male, because there were 70% males in the data. If you didn't think about it carefully, you just said, I'm going to take the average weight and put it in there for all the missing ones. You've now changed the score for this person to be much more like males than it would be for females. And that could be, again, a bias that you created. That didn't come with the data. That was what you did. As us designing. So there are many such things that we do that result in these biases. The last thing that's not a machine learning problem, but let's say you built a perfect system to predict the risk of somebody getting COVID perfectly, or vulnerability. But then the way you allocated the vaccines, you started calling people to tell them, they've been selected to get a vaccine, and they have to make an appointment. And let's say you chose, to call people in just one language. Let's say you decided, I'm going to just make calls in Hindi. That's it. Or English, even worse. So your system, your machine learning system is perfectly fair, but your way of allocating or actions are not fair, because you're choosing to make it to they take these actions in a way that result in biased outcomes, and that's not a problem with the data or the machine learning, but it's a problem in how you design the action. And so all of these things, the world, the data, the machine learning systems you built, and the actions you took, results in bias in the outcomes, and that's what we really care about. Is we care about fixing all of them, because we care about the outcomes to be fair. And so let me kind of give you a last example of, so here's kind of an example of, so we have sort of, for those of you who are kind of building these types of systems, we have some tools that we've built and that can detect some of these biases and kind of tell you, the model that you've built is biased. It's biased in this way for these types of people, so don't use it. And so there's a bunch of things that you can I'll send the slides over to Saurabh, and you can look up some of these tools. And so often what we're sort of, when we work on these projects, typically we sort of define some performance metric, and we build a bunch of models and we say, I'm going to pick this yellow model because it's the best. And the way we work on these projects is we also have this other dimension, which is bias. And so then we say, okay, well, the yellow one has the best performance, but it also has high bias. And maybe we should pick this green one because the green one is a little bit worse in performance, but much, much, much better in terms of bias. And so this is made up, but let me kind of show you some real examples, right? So this is a real project. And this is looking at how accurate on the x-axis the system is, and the y-axis is bias based on gender. So the higher a model, each dot is a machine learning model, the higher it is, the more biased. And the more here, so a model here would be the really well-performing and unbiased model. It turns out that these two models are the best performing models. And, this one is twice as biased so it's a value 2, twice as biased for females than for males. And the question is, should we pick this one? Or maybe we can pick this one that's a little bit less biased without losing anything in performance. Or we can pick this one. Because we lose performance, but we also gain a lot more in fairness. Or we can pick, some of the other ones that we can keep coming down. So that's one way to think about when you're building these systems, is what trade-off do you care about? And is there a trade-off? Because by building, if you just pick the best one in performance, you wouldn't even see the choices that you have. Right? So here's an example of a project that we were working on with a hospital on predicting who's going to get diabetes in the next 3 years, because the doctors want to know if we can tell them that this person will get diabetes in the next 3 years, they can work with them to change their lifestyle, their eating behavior, their other behaviors, and they need this much time. They need 3 years to actually change the behavior. So they want us to build a system. And what they find is that they want to build a system that's not just accurate, they want it to be fair to different types of people. And so here's kind of, here's what the system, here are the results, what they look like, right? So this is a graph for what the bias is. The higher the bar, the higher the bias. And so this is sort of saying, this is what the hospital does today without a machine learning system. This is just doctors decide based on their experience, that person is likely to have diabetes, so they're gonna tag that person. And what we find is that based on so this is for age, that they are much worse for older people, 40, 70 and 70 plus. They're much worse for certain race. So this is people who are Native American, or again Native Hawaiian, and they're about equally right for male and female. So this is the doctors as they do today. This is no computers, no machine learning. And so then we said, okay, let's build a machine learning system to do the same prediction. And so here's what happens. We built a machine learning system, and we initially focused it not on being fair, but just on being as accurate as possible. So here's what happens. The orange lines are the ones that we had before, basically. It's the doctors by themselves. The blue is the machine learning system that is focused on being the most accurate. And if you notice that machine learning one is better, the blue line is always lower than the orange line for every group. So this machine learning system does better for every group than the doctors. Except what you notice here is, so let's say the doctor is equally correct for both 40 to 70 and 70 plus. Like they make equal amount of mistakes. They make a lot of mistakes, but they're equal number of mistakes. whereas the system makes more mistakes for 70 plus people than 40 to 70. Same over here, right? So if you now look at these two groups, white and unspecified, the doctors make about the same number of mistakes, but the machine learning system makes much fewer mistakes for white people. And so the question here is, what do we want the system to do? Do we want it to be better for everyone, or do we want it to be equal for everyone? Right? Because if we implement the system, the blue one, what it's going to do is it will reduce the diabetes rate for everyone in the country, in the city in this case, but it will have a higher diabetes rate for old people than for younger people. So we'll see old people having more diabetes than young people, whereas in this system, the orange one, we see equal. And so one system is better for everyone. The other system is more fair for everyone. And again, we have to choose which one do we use. And it's not my choice because I'm just helping them develop the system. It's a choice that we have to make, as a society. And this is where, if you work on these types of projects, it becomes, these conversations become kind of somewhat about philosophy, somewhat about ethics, somewhat about law, and not, the machine learning is there to help you do what you decide you want the world to look like. It doesn't help you figure out what the world should look like. It helps you get there. So that's kind of something to keep in mind, is as you're making these really important decisions about people's lives, who should decide this? Who should tell you which system to build? Because today, that's not, you're not being told these things. You're being told, can you build a system that predicts who's at risk of diabetes? Well, that's easy, but there are many such systems you can build. Which one should you build? Which one should be, and again, so just a quick version for, I know I'm over time, I'm going to wrap up in a couple of minutes. What we tried to do was say, okay, what if we tried to build a system that was best for Hispanic people, so people from Latin America and South America. And so this light blue is the one that it's now better for Hispanic people here than the previous one. So we can make it better, but at some cost. When we make things better for this group, they get worse for this group, and they get worse for this group, and they get better for this group, but they get worse for this group, right? So, and then we say, okay, what if we built a system that was as fair as possible for every racial group? And that's this color one, right? So all of these are about the same now. But how did that happen? We had to make it worse for Black people, worse for Hispanic people, worse for a bunch of people in order to make it equal. Right? And so it's not fair to them. Which way? And again, the question is, who decides what these, to sort of your question, Nick, who decides what these groups should be? How should we say that they should be, these racial groups, and not gender, and not location? Should it be each neighborhood, each city? Those are all open questions, right? Like we have to kind of decide as a society what these answers are, as opposed to machine learning deciding that. And so here's another example of the same phenomena, right? This is another, if you sort of think of this as, if you built a system that was the most efficient system, it tried to help the most people, it was the most accurate system. Let's say that the rate for, this is not diabetes, but assume for now that the rate for diabetes for Hispanic people is high and the rate for diabetes for white people is low. If you built the most efficient system, and let's say that the most efficient system was more accurate for white people than for Hispanic people. In this case, for now, just to make it easier, think of it as, maybe it's female and male. And so let's say the diabetes rate for female was higher than male, and you built a system that was more accurate for males, the overall rate goes down for both when you help them, but it goes down faster for one group than the other. So it makes things worse, for the difference becomes much worse. But you could say, well, I can build a system that's equally correct for both. But if I do that, it might be more expensive because it's not the most efficient system now. And so, but it keeps this difference the same. And over time, it reduces both, but it reduces them equally. Or you can build a system that's better for the group that needs more help, right? Maybe what you want to build is this system number 3, which is the group, the blue group needs more help because they have more. That's what we're talking about for COVID. If a group has a higher rate vulnerability, maybe we should build a system that is more accurate for them. And so over time, it reduces the rate of, in this case, this is going back to jail, to be equal in 5 years and 6 years. And that might cost you a little bit more. But again, as a society, we have to decide, do we want system number 1, which is the efficient, helps the most number of people, but helps different types of people differently and makes things worse for certain people? Do we want to build a system that's equally correct for both, even though they don't have equal needs? Or do we want to build a system that is helping people who are more vulnerable, who have more needs more, and that might cost us more? And those, again, are like, we can build all of them with the tools that we have. We have to decide which one we care about and which one we want to build. So yeah, so that's kind of, yeah, this is just summary, right? Is we've got all these different tools, machine learning, AI, that allow us to build these types of systems that can be efficient, that can be effective. And the question is, we should really be building them to make sure that they are fair, because that's really important for us as society. And working with sort of governments and NGOs is a way to sort of solve these types of problems. But these problems can't be solved, in a lab, in a university. They have to be solved in collaboration. So that's kind of, those were examples that we were doing this type of work. And so if people are interested in kind of doing these types of projects, this is just something we launched a few months ago, which is a website where it's a platform where nonprofits post projects for data science, and then volunteers come in and help work on those projects. So if any of you are interested, go take a look there, sign up. It's fairly new, so we're still working on it, but you can sort of try it out and see if you want to get involved. And yeah, happy to take questions now, but also, feel free to email me, but also for pretty much all projects, the code is all open source and it's on GitHub. So anybody who's interested in that, feel free to take a look. And yeah, happy to take questions.
Thank you, Rayid. Brilliant as always. Really enjoyed your talk. While the others are thinking up their questions, to follow up on my point about how do you compare groups, right, or even define the groups to be compared. I lived for a number of years, as you know, in Northern Ireland, where the narrative was that Catholics and Protestants are at each other's throats. And people always blame religion for all conflict. And I am one believe that if you remove religion, people will find a reason to fight. I'm a Manchester United fan and you're a Liverpool fan, so you don't deserve to live, right? Now, as we dig into data, the way you're doing, are we helping narratives, where people always want to feel that they are hard done by, right? The Democrats win. The Republicans are saying there's this foul play. The next year, it's the other way around, right? So what do you do?
Right. No, I think I have a slightly different framing, right? So I'm with you that a lot of these groupings, it may not be good to kind of silo people put into these groups, because then it's making things worse, right? The way I'm sort of thinking of a slightly different way. And my way of thinking is there are systemic issues in the world that happen to be based on things that you cannot change. Might be the caste system in India, racial things in the US, economic status all over the world. While that's not the case with Man U versus Chelsea fans, right? Like, yeah, they have issues among each other, but the world is systemically not doing horrible things to Chelsea fans, and because so I think my framing is that the world is treating you differently, and we have to make sure that when we allocate resources to help people, we take that into account, and we make sure that the goal is to get people to an equal state at the end. Um, and once we're there, so the idea is not that you continue doing this forever, right? Once we've reached some level of equity, then you adjust it. So this is not a one-time thing, it's a continuous thing where and it might be, as you say, it might be that 5 years, 10 years, 15 years from now, we will have new groups to worry about. It's not going to be racial groups. Maybe it's people who wear glasses versus who don't wear glasses, or tall people or short. Like, we will come up with these new systemic issues, and then we'll have to adjust our systems to deal with it. So I agree with you, but I think right now we have an idea of some of these people who are being affected. So let's focus on that and try to fix those gaps, and then let's move on to other ones.
Doesn't that also then help the narrative, right, from the other side? So, right now we know that Black people are much more likely to end up in jail again. And the belief is that there's a bias there, right, that causes that. But at the same time, if we work towards bringing down that rate, then there's going to be, the white community that's going to say, that's discrimination against us, right? So, and of course, we've seen that all over the world, right? That's just an example. So,
that's right. Yeah. No,
are
absolutely.
you making those voices more powerful by intervening?
Yeah, absolutely, right. So, like, I often talk about the phrase that's used in this world is reverse discrimination, right? You're doing reverse discrimination to counter the previous discrimination, and I think that's okay. That's but again, it's not okay forever, right? It's okay up to the point where you have gotten to equality, and then you can start thinking about it differently. But I think until we get there, we're going to have to fix some of these issues, because otherwise you can never get to a place where there is any sort of equality. And yeah, there is a risk that people are going to be against it. But I think that's something we're going to have to work on explaining why this is important, and get there. But we have to do it.
In a greater polarized world that doesn't allow people to change their views. Right. Well, it's good to have a challenging problem to work on, right? So,
yeah, get rid of Facebook. Maybe that's going to.
Partha, you have a question? Do you want to unmute and ask it? Or maybe we can just. So, will a data science solution going to be cost effective for relatively poor countries?
A little more to be a little more elaborative. Like, for an example, say if I want to build a simple traffic solution system, we need to install cameras, and plenty of them. And also in the background, there will be some high-end computation devices. And let's not tell about the costly data scientists like us who will be there. They will also be involved in that project. So overall cost, it is something. And so for relatively poor countries, like say India, in fact, remote regions of India, maybe those regions need more data science solution than the first world countries. And so.
Absolutely. Yeah. So it will cost, it will cost some money. It's going to cost money to collect data. It's going to cost money to do the analysis. It's going to cost money to pay the people. And the question is, what's the value that's providing, right? And so all of those things are also true for all the businesses that are doing work in India and doing data science, right? They collect data. They spend a lot of money collecting data. They have GPUs to do analysis, and they hire a lot of people and pay them a lot of money because they think that it generates value for them. And so that's how I would think about it, is if we as a society, as a world, think that these problems are worth solving, that they provide us with value, then we have to figure out a way to pay for them, whether it's taxing, which, not so I grew up in Pakistan, right? Not many people pay taxes, or not many rich people pay taxes. People pay taxes, but people who are rich don't pay taxes. And so maybe we should work on that problem and make them pay taxes so that we can do this type of stuff. Or we have all these companies that are coming to India and setting up all these labs and all these companies, and maybe we should tax them. On every data scientist you hire, you have to give X% of their salary or time. Maybe 10% of every data scientist time should be given to people to do this type of work. And partially it's people like you who should be asking for that when you interview with these companies and say, I'll help you do whatever useless thing you want me to do because you'll pay me to do it and you'll train me, but I also want to do this thing. So how are you going to help me do that? Because I think there's so much demand right now for people with these skills. We have to use that demand and say, we also care about other things. We're not just, so I think, yes, these things cost money, but they are much more valuable than a lot of other things. And we spend money on, I think the thing about governments, right? Governments are spending a lot of money on stuff. They're just not necessarily being smart about how they're spending their money. So if we can convince them that instead of spending this much money on education, they should take 10% of that money and use it to figure out how to be smart, and then allocate the rest of 90% using that 10%, maybe that's another way, right? So I think a lot of it is really showing them what's possible. So a lot of the projects that I talk about are really, they weren't nicely defined projects that somebody came to us with and said, can you help us solve this? They were very vague and very fuzzy. And so we had to help them figure out what they really need and what they want. And I think that's what's needed right now, is showing them an example of what can be done, making them realize the value of doing this, and then sort of going in and saying, we need to do more of this. So not easy, but we have to do it.
Thank you, sir.
Thank you, Rayid. There is a question that's probably going to take more than 5 minutes to answer here, which is, can you go deeper into what are the parameters and the data? And I think that's probably a bigger conversation than
longer. Yeah, I think the last, one of the questions about sort of what are the readings you should be doing, what are the practical readings, and I think that's a really good question, because we're at a place right now where a lot of the readings that you have, a lot of textbooks, a lot of papers, are really about like this building models, right? And that's the easy part. And it's sort of, how do we define the problem? How do we think about the overall system? How do they connect together? Once you've built the model, you can build 3 million models. How do you pick the one to use tomorrow? How do you update it? How do you monitor it? How do you get people to actually do something based on the model? How do you communicate what the model is actually doing? Like, all of those things are what the practical stuff that makes the actual difference. And to be honest, there isn't that much, there aren't any textbooks I can recommend to you, unfortunately. A lot of it is, what I would do is, read things, but also the best way to do it is to try to get involved in projects, like whether it's with other people who are doing this work, whether it's, the more experience you get doing these things, the more, that's really the best way to do it. And hopefully, in the next few years that changes, right? I think we as a field need a lot more practical training programs rather than more methods and academic, more courses that tell you what a neural network is and what a random forest is. And that's useful to know. You should know that. But then how do you use it? And don't feel like you are in that position. I teach, PhD students here in machine learning, and most of them have no idea how to use machine learning. They can all tell you what the math is, what the stats is. They can't use, and that's what we're teaching them, right? We're teaching them, historically, we've taught them everything about the algorithms and the models. And now we're also trying to teach them about how do you solve a real problem? So it's not just that it doesn't exist in certain places. It doesn't exist in most places, and that's something, again, we have to figure out how to fix.
Thank you, Rayid. I know it's well past midnight on your end now, so thank you again for a wonderful talk and sharing your thoughts with us. I think it's really going to motivate people here to think differently about data science. And the next speaker, in fact, is somebody who's been pioneering the building of AI for India, Shailesh Kumar, and he's also going to give an overview around the kind of work that they're doing. So it follows really well from your talk. So thank you for creating a great start to this program here. And I hope that we'll bring you back often to talk to us and motivate us. And also, we hope that we can work on projects together in the future. But,
absolutely. No, thank you. And people feel free to email me if I can answer any questions. But it was good chatting with you guys, and I'll talk to you later.
Great. Thanks, Ryan. Thanks. Bye. So the next speaker, I'm really proud to invite Dr. Shailesh Kumar. Dr. Shailesh Kumar has had an amazing journey from when he did his PhD at the